Fellas, what's up? Got an awesome little video here today, and it's basically on the subject of a comment made by this individual here, and it reads, anyone can make a burner that outputs 2 million BTUs an hour, but how do you use that much heat? Give me something that puts out a clean burn at 15 to 20,000 BTUs an hour that I can use. Brother, I got you faded. Check it out. Just did some testing on this device right here. I've taken the nozzle off so it don't roast itself, but we were running at a 1/4 liter every 26 minutes. It was running so slow I didn't want to burn a whole liter of fuel. It comes out to 0.57 liters per hour at the airflow that I had going on, which was very low. That was done with this nozzle. And we're going to kind of tear it down and observe the foul up after burning a liter of oil. We burned about a liter of oil in the test in total, and I wanted to observe the fouling. This nozzle was still performing just fine, and I would imagine it would take quite a bit for some buildup to cover up that annular jet that we see there, that small little space between that center tube. There is a little bit of fouling inside the device itself. So this is where I'm at, fellas. We're gonna do some toggling one last time for our nozzle position acquisition. It's a pretty good chunk of foul up right there that would probably render the device inoperable after several hours of use. It was already starting to act up after just a single hour. So we might need to play with that a little bit. In my opinion, the burn that we are going to be looking at or have already seen, I'm not sure yet, I'm thinking it was a little bit too rich. So I'm going to do some messing around with the fuel ratio here in the next couple of tests. I just wanted to get an approximate fuel consumption baseline of what this thing does, because that comment, really kind of hit home with me. I agree with this guy so much, because I've tried to build waste oil burners that burn under 1 liter per hour. Typically, the ones that I build can barely do 4 liters per hour. 4 liters per hour, and they're wanting to go out on me. So being able to hit under 1 liter per hour today is a huge benchmark in my design journey. Building something this small is extremely hard to do, guys, and it may look easy after seeing me do it and then you go try it, but I didn't just come up with this little configuration the first time around. I wasted a lot of time and a lot of effort getting this far with this project. So we're kind of shifting gears a little bit on the project. I started building these burners that were getting exceedingly hotter and hotter, and I realized something, that I kind of needed to stop where I was, because all the fuel was being burnt inside the burner like a jet engine with very little exhaust coming out the back, and I don't want that. We want to use this to do work. If you're using it for a heating application, that'd be fine, but these videos are for the most part tailored to people who are using these devices for jobs other than heating, such as working with metals, things like that. But this was definitely a pretty cool little experiment. I'm happy with the way this thing works. I have not had any time to do much experimenting with nozzle position. The footage I examined concluded that the position we see in this video was the optimum for stability. Performance, maybe not so, but I wanted a stable flame. So the configuration we're looking at today is probably the most stable configuration achievable based on the footage that I've seen in the last test. However, that last test did not have this cowling. I added this on here, and I don't know if I'd like it or not yet. It does not breathe air at high flow rates. In fact, we're looking at that too. I was hoping a little bit of air would be brought in through this way, through Bernoulli's principle. Bernoulli's, however you say that guy's name. Yeah, that's where we are. This is turning out to be a cool experiment. As I said, I'm backing off of burning exceedingly hotter and hotter burners for now because I'm not getting enough flame sticking out the front. However, that is very useful in some applications. My idea is I want to get a flame about this far sticking out the thing that's very soot free, because I'm going to be doing some testing with some steam coils, some things like this. I'm going to get some more stainless steel tubing, but I want to try this copper one first. And you don't want soot getting on these things, fouling everything up. You want a super hot flame, and then that's it. So I'm worried about fouling up my gear, my steam equipment, without having a hot enough waste oil burner flame. And a small burner this way is definitely ideal for some of the machines I have in mind. At any rate, this is a very interesting little device. I am very pleased. It has revived my enthusiasm for the project altogether. This little thing right here. Very cool, very cheap. The back dome area that I've added, I was hoping would add a vortex to help maintain combustion, but from what I've observed, it's not quite doing that. In fact, the entire area appears to be a vacuum, as if the air is just being drawn out of it, and it appears nothing is going on in that region. And the fact that it doesn't even get very hot kind of suggests the same, or corroborates that theory, I guess I was trying to say. So we're going to do some more testing with a lower burn than what we saw. We're going to do half of what we've seen. So we're going to try a 2500 watt flame, which is just freaking unheard of in the waste oil burner world. As that individual has said, we're mostly seeing devices in the million BTU range, which is insane. Some of the ones you see in my videos, however, the recent ones that you have seen are, I believe, in the 40,000 watt area. So 40,000 watts times 3.41 is what the equation would come to. Here, I've got a calculator up. Let's see. 40,000 watts is 4 liters per hour. And that comes out to 136,000 BTUs. So that's the region a lot of my equipment operates in. I go up to 60,000 watts. I do have devices in the 200,000 kilowatt range, but I no longer run that device. I've taken it apart subsequent to coming to the conclusion that what this gentleman said is absolutely correct. What am I gonna do with a million freaking BTUs? Not too much. I'm not smelting a car.